Alrighty, guys, what's up? It's Daddy here again tonight, and I'm excited to be back with you. I apologize for the infrequency with which I've been making videos recently. Um, just had a lot of life stuff going on, but this is one I'm excited to do. It's one I've been promising to do for a while. This is going to be a comparison between the P40, P100, and the RTX 3090 with the new BenchDaddi benchmarking suite I've been working on. Finally got all that lined out, and now I'm going to show you how I've used it to benchmark and do kind of a performance comparison between these three GPUs. So we'll go ahead and hop into that in just a second. But before we do, I have a couple of housekeeping things or just interesting things and um, some things you should probably know before we get into the video. The first one is I've used quite a few data visualization softwares, uh, in the last 5 years since I've gotten into data science and machine learning and deep learning and so on. And I don't know how I've missed this, but there is one I'm using now. It's called Google Looker Studio, and I really, really like it. Don't know why I hadn't heard about it until now, but it's called Looker Studio, and this is what it looks like. You can literally search Looker Studio, and it's the former Google Data Studio platform. But I mean, normally I would use Power BI, but since I'm traveling and I'm on a Mac, I can't download Power BI desktop, and I don't want to pay for the um, cloud-based version. Tableau is super expensive, and so is Click and some of the others. So anyway, this is a really nice alternative, free data visualization platform that's, in my opinion, pretty performant. It looks really nice. It's super easy to use. Um, so if you're interested, let me know, and I will make a video on how to use Looker Studio and some more of the in-depth benefits of how to set things up and kind of how to go through that. But the thing I really like about it too is if you already use the Google Drive ecosystem or the Google ecosystem in general, you can link this with the Google Drive, you can link this with Google Sheets, you can link this with a lot of things that are easily accessible in that platform, um, and you're already good to go. So for me, I have this large uh, CSV, and then I uploaded it, and now it's a Google Sheets document. And this is where all the data is coming from this. So of course, I'll link this in the video description as well as a link to this and a link to the GitHub repository itself for the BenchDaddi benchmark suite. So all that stuff will be available to you in the video description. But anyway, without further ado, let's go ahead and get into some of the specifics, and then we will maybe touch on some of these other things as we go through the video. But the way I want to cover this is it's important to understand the test environment, because this is going to have an effect on the performance results. So, whatever server, whatever workstation, laptop, whatever it is that you're running this on, all those different hardware components are going to have an impact on the overall performance of your GPU in some way or another. So we're going to cover that first. We're going to look at the actual GPU specs. Um, this is the model configurations, so I'll edit that in just a second. Um, but we're going to look at the broad performance in terms of like overall performance, and then we're going to take a look at things more granularly. We're going to look at data transfer because that's kind of an important thing to keep in mind, and then also memory usage. So I'm going to go ahead and correct that mistake real quick. All right, so we'll start with test environment specifications. So for me, and if you've been following the channel for any length of time, you know that for now, my main machine that I do a lot of my machine learning related work on is a Supermicro 4028 GR-TRT with a X10 DRG-OT plus minus CPU motherboard. So that's, I have some other videos setting that up if you're curious about that particular machine. But basically, it's a 4U server that is designed to hold 8 GPUs or up to 8 GPUs, and is designed basically for ML and DL applications. So inside of that machine, there is two Xenon E5 2699 V4 CPUs, the clock speed of 2.2 gigahertz. Each one has 22 physical cores, so 44 logical cores, and then there's two of those, so that's 88 total logical cores. As far as RAM goes, I'm using Hynix, I think is how you pronounce that. I'm honestly not 100% sure. It's a DDR4 RAM, and it's configured to 1866. I think that's mega. Hold on, I always forget this. Yeah, so that's mega transfers. MT, mega transfers per second. Um, Sorry about that, guys. And then the RAM modules, these are 64 gigabytes apiece, and there's 24 of those, so about a 1.5 terabytes of RAM. It's Ubuntu 2204 for the operating system, and then for the interconnect technology, it's going to be PCI 3.0. So this should give you a good idea of the specs of the machine and kind of what we're operating on. So this hopefully will allow you to, you know, understand the context of how all these results are being generated. And, you know, if you're getting different results, it's probably, could be because you have a different environment. And, you know, if eventually the goal is to have a bunch of you guys try this and then upload some of your results so we can do, you know, analysis on not just the GPUs but also the CPUs and other hardware that they're run with. So I think that'd be pretty cool. So I'm also going to put up a spreadsheet as well, so that if you guys want to run this locally, you guys can upload all of your information into the Google Sheet, and then, you know, I can make a bigger and more comprehensive um, evaluation for a lot of different people and all their information. So I think that would be cool. Make this kind of a collaborative project. But anyway, so that's test environment. And then the next thing we need to address is the GBU specifications. So um, we're looking at the P40, the P100, and the RTX 3090. And I always like to keep things price conscious. You know, everything that I try to do is in terms of not only performance but also price, because I think that's incredibly important to always keep that in mind. You know, what performance you're actually paying for, or I guess what performance you're getting for your dollars. So as of today, this is what you could buy a P40, P100, and 3090 on eBay from a reasonable, what I would consider reputable seller, like a wholesaler that has good reviews, basically. And this is what you could actually buy them for. So you could buy P40 for $162, approximately P100 for about 150 bucks, and then the RTX 3090 for about $820. So this GPU compatibility, this is a basically a metric to let you know the GPU and like the model. So some of these have like iterative releases that have different performance specifications. So this is the like P40 6.1 tells you specifically like what model this GPU like what submodel, I guess you could say, this GPU actually is. And then it gives you a better idea of the like theoretical specs associated. Um, and then we have, of course, the VRAM size. So P40 and the 3090 are going to have 24 gigs of VRAM. The P100 is only going to have 16. They also have different VRAM types. So we have the GDDR5 for the P40, HBM2 for the P100, and then the GDDRX or R6X for the 3090. And then, of course, they all have different bandwidth. So P40 has the lowest at about 350 gigabits a second. The P100 has the middle at 730-ish gigabits a second. And then the RTX 3090 has the most at 940 approximate gigabits a second. TDP, so how much power does this actually need, or max power does this need to run? 250 watts a piece for the Tesla GPUs, and then the RTX 3090 is a bit power hungry at 350 watts. These two are not NVLink compatible. And then this one is, and I am actually using it in this case. So this is a yes, it is compatible, or uh, is made to be used with NVLink, and it is also actually implemented for these tests with NVLink. And I think it's always good to understand the theoretical specs. This is all kind of we can kind of confirm or deny these with the actual results coming up. So the P40 is basically trash for FP16 or half precision. It also has pretty bad uh, double precision, but it has um, pretty good single performance, or FP32. Um, is actually better than the P100. So, for a lot of people that actually aren't specifically configuring the GPUs for mixed precision or using them for scientific calculations that really need that double precision, this is actually a pretty good way to go. Um, because this is how a lot of models are made to run by default. So, for a lot of people, this actually is going to provide great performance and is actually going to be a better choice than the P100. But as you can see, the P100 is the most well-rounded, actually, of all. It has by far and away, the best um, double precision. It also has, it has half precision, and it uh, it does fairly comparably in terms of single precision performance. Um, when compared with the P40. So, good, well-rounded option, has high bandwidth. So, these two really are two great options, I think, for most people that are getting into machine learning and deep learning. I really love these GPUs a lot, and I think they have a ton of price to performance. And we'll see that coming up in more detail. One thing to note, though, these do not have tensor cores, so we'll see later how that actually affects um, the half precision performance, the FP16 performance. The RTX 3090 does, and we'll actually see later that this provides, when you run in mixed precision, it actually provides quite a bit of a performance increase. So that's certainly one thing to keep in mind. As you can see here, it's tied, exactly even for half precision and single precision, and then it's pretty bad at double precision. So that's a pretty good overview of the GPUs from a theoretical perspective. Can't speak tonight. All right, so for the model configurations, we're looking at this point, the benchmark uses ResNet, or incorporates ResNet, an LSTM, and BERT. So this is from PyTorch, this is from Hugging Face, and this is just basically built out of PyTorch baser modules. So I couldn't find a good pre-built implementation of the LSTM, but I really wanted to, and again, I go into more detail into this in another video on the benchmark itself, but I wanted to, at least for the initial iteration of this kind of benchmarking suite, I wanted to look at the three different architectures: the RNNs, CNNs, and then transformers, and then for different applications. So this actually has, so this is looking at image data. So this is looking at CFAR 10. So I'll go ahead and flip over here. So this is the repo, and has a big write-up. So if you're curious, you can look at the code and watch the YouTube explanation, and then you can read through this. But basically, ResNet is looking at the CFAR 10 data set. So that's 10 different classes. And I forget how many images, but it's a substantial amount. And then what I do is, in the code, I resize them to 256 by 256 to kind of make this more of a substantial load on the GPUs. So by default, I think they're like 36 by 36 or something really small, but we resize them up just arbitrarily to basically increase the load and the data transfer stress on the GPUs and the overall system. So one thing to note there, this the BERT, we're using the IMDb dataset. That's pretty standard, and it's basically for sentiment analysis, like positive or negative, for these like text captions for these movies. So this is more akin to what everybody's fascinated with now with LLMs. And then um, the LSTM is looking at time series data, so just tabular time series data. And this I think has like 2.5 million rows, and it's electric power grid consumption data on UCI ML repos, like publicly available data sets. So anyway, if you want more information, feel free to check this out or drop a comments, and I can go over these data sets in more detail. If you're interested. But yeah, the major configurations you need to be aware of is the model for each of these models. We run 3 epochs. The learning rates are listed here, and then each of them have batch sizes that I played around with it, and these kind of seem to make sense in terms of like GPU loading. I think actually I should have done a better job with the LSTM here, and I should have increased the batch size, and I should have gotten a bigger data set because the overall load from the LSTM on the GPU is pretty small. I should have also increased the sequence length, um, but those are things I can do in the future, or you guys can do, and maybe make suggestions as what might be good ideas to do here. Um, and then the number of data load workers is 4 across the board. And then, of course, I already showed you, but you can find the repo here and go into more detail in the code and read through the README and get a lot more information that way. All right, so this is the moment we have all been waiting for, and we're gonna go over the broad performance. So what we've done here, what I've done here is I've kind of run um, every different combination of possibilities. So uh, I've run each of the models, and then at each precision, so mixed and single, and then also training and testing. So basically, training is actually, like it says, training the model, and then testing, you could think of it as evaluation or inference or whatever you want, but we're basically taking the trained model and we're feeding it batches of data, and we're asking it to make predictions. That's what this testing is equivalent to. So I just use classic training and test, but some people, uh, you know, uh, might call this inference or evaluation, whatever, and there's nuance there, but the point I'm getting at is that this is making predictions and this is actually training the model. So I wanted to show how the performance is different in each of those scenarios. All right, so the first thing we want to look at is scaled throughput by GPU. And I thought this was probably the best metric to evaluate GPUs against each other, because it's basically taking the number of samples, and I'll just show how I calculated this really quick, so it'll make more sense. But basically, um, so the throughput is basically samples per second. Okay, so it varies widely from model to model. So this is probably the LSTM. The throughput was quite high. It's like 300,000. And then this is probably BERT, and the throughput was quite low, like at 67 like tokens a second. I'm just using samples as a general term to say that like pieces of data processed per second, basically, whether that's an image or text, string, or whatever the case is, in these different models and scenarios. But there's no good way to actually directly compare these. So what I did is I took the CPU performance, so base level CPU performance, and then I divided each of the other relevant categories. So for example, if it's like ResNet, okay, so the CPU performance for ResNet for training and test is divided, like the each of those CPU values are divided by the all of the other scenarios. So that basically scales like how much better are you than the base level CPU. So as you can see, this is like all these are one because these are the base cases, if you will. and this is 9 times, but whatever this one is 9 times better than the CPU. This is 6 times better than the CPU performance 7, and so on and so on. I did this for execution time or total execution time. I did this also for uh, throughput, CPU scaled. So that's what, when it says CPU scaled, that's what it actually means. And this is just the total time it took to run for execution time. And then this is the total number of samples it was able to process per second. So, and those are scaled relative to the CPU. Um, and then that's what we're actually using here to benchmark, because that's, I think, in my opinion, the best way to do it. And then another thing to note is that the execution time and then the the throughput, like the scaled values, are almost exactly the same. So I just picked one because you're going to get a pretty good idea of performance, whichever one you look at. They're very similar across the board in about like 99% of the cases. So rather than showing you two redundant graphs, I just figured I would show you one, and I think throughput just makes the most sense. Um, so yeah, so that's what we're looking at here. Um, and as you can see, CPU is 1. And then all of these are averaged across these different categories. So right now we're looking at all the models. We're looking at both mixed and um, single precision. And then we're also looking at across training and test. So this is just across the board. How did it do? Um, so with the P40, um, and these are stacked here. So this is then the like turquoise here. We have one GPU situation, and then in the like blue, darker blue, we have a 2 GPU situation. So this just stacked here, just to kind of save space. Um, but for the single, we can see that we're basically about 5.5 times as good as what the CPU can do for the P40. And then for 2, we're about 10, or call it 11 times as good as what the CPU can do, just across the board on average. Same thing, or not same thing, but with the P100, we're a little bit better at about 6.5, and then 12 times with the 2 GPU scenario. And then with the RTX 3090, we are significantly better. So we're almost 3 times as good as the P100 and over 3 times as good as the P40. Actually, almost exactly 3 times as good as the P40 with in the single GPU configuration, and then with double GPU configuration, we are about 30 times as good as the CPU, about 3 times as good as the P40, and two and some change, closer to 3 times as good as the P100. So I guess in summary, P40 is kind of the laggard here overall. The P100 is the most performant of these two lower level, like I would say more budget option GPUs. However, you know, with the uh, performance being so close, I personally would rather have uh, the higher VRAM, especially if you're not running a lot of like mixed precision operations. If you're trying to run mixed precision and you really are interested in LLMs, then this would probably be a better way to go. And we can explore that in a moment, whether it actually is or is not. But in theory, this should be better because it has better half precision performance, and you could run your uh, run LLMs with that. You could fit more into memory. You could compute faster, et cetera, et cetera. Um, but these don't have tensor cores, so that we'll see in a minute that doesn't really actually hold if you're using mixed precision. You could cast everything down to FP16, and then you may actually see a performance boost, but then you're probably going to break some things in the model itself. So there's always trade-offs here. But overall, I would say for most people, the P40 is probably going to be a better option because of the higher VRAM. And then I'll make the case later on when we see some more metrics. And then the RTX 3090, we can see far and away outperforms, and it has tensor cores, so we'll see in a little bit as well, how it's able to even do better when we um, use mixed precision. And of course, you can get even more granular. I'm just looking at this from a high level perspective, but for the sake of time in this video, I'm not going to dive into all the nuances, but you can filter this for ResNet, and you can see the specific performance here. In terms of this model, you can also look at just mixed precision, and you can see that when you factor in mixed precision, you get actually better than 3 times performance over the P40. So, my point is you can get more specific here and look at these all kinds of ways. But I'm just trying to keep this a bit general for the sake of time. Um, but I'm going to provide this notebook for you so that you can go through and you can look at whatever interests you, um, and go from there. So I'm just going to reset this. And then one last thing that you can choose again is the test and training. So, what if you're more concerned about training performance? Well, you can see specifically, in terms of training, how does one GPU stack up to the other, and so on and so forth. Okay, so we'll look at holistically again here. And then again, I always try to keep things in terms of dollars and cents. So uh, this is the scaled value. So how many times better are we than the CPU, scaled by the cost of the CPU. So basically, in this case, since there's one or two, it's the cost of one GPU or the cost of two GPUs. Um, so what this is telling you is how much are you actually paying per 1 times better than the CPU, or so, like, how much are you paying to be like one increment better than the CPU? So like in this case, like it would cost you $141 to get 1 times or like 1x performance, uh, or 2x performance basically, and then that it would go in those increments, if that makes sense. This is basically just a way to understand, like, in a scaled way, how much you're paying for one CPU performance. I guess that's the the best way to say that. But as you can see, you're paying a lot. Like with the fancier the GPU, the more you're paying for, um, at least in this case, one CPU, like CPU level increments of performance. So, you know, still, it it seems that the P40 and the P100 are the cheapest ways to get better than CPU performance. So it's the best way to say it. I mean, these, you know, in general are the best options as far as from a cost perspective that you're going to be able to find for training models for ML and DL. Now, there are a lot of caveats there. Depends on the size of the things that you want to train. Depends on how quickly you want to train them. And it depends a lot on your budget. And depends on a lot on your goals. So this is kind of the goal of this video and this benchmarking, is to help people figure out what you actually need for your particular use cases. Um, you know, what are you actually paying for performance? Because in my experience, GPU, or really hardware in general, is just a really complicated, convoluted, um, you know, thing in general, and there's a lot of, uh, I guess I don't want to say secrecy because it's not, but it's just a lot of, it's hard to find reliable information, and it's hard to make data-driven decisions in this area. So that's kind of what I'm trying to do, is help people make better informed decisions about what kind of computing they actually need and what it's going to cost, and in what scenarios it's the most beneficial. So So, okay, cool. That's a pretty good overview of the broad performance. Now we're going to get a bit more granular, and we're going to look at the kind of differences between training and test, and then the different precisions. Um, so, as a oh, hold on, I forgot to average these. Just give me 1 second. All right, guys, sorry about that. I had those summed for some reason on accident. But anyway, now this is averaged across the models and across the number of GPUs. Um, so what I wanted to get at here is there can be differences in training and testing for particular GPUs, for example, across various models. So in this case, we have, um, it seems like better performance across the board for training with the RTX 3090, the P100, and the P40. Although um, it's the the gap lowers a bit when we talk to the P100 and the P40. There's a bit wider gap here between training and testing when we're looking at the RTX 3090. And then of course you could get more granular, and you can look at just LSTM, and you can see that in this case there is a huge difference between testing and training. And in this case, it actually does much better for testing. Again, caveat being that this may be because of the data set I chose and the fact that it didn't really put that much strain on the GPU. So these results may be a little bit skewed. But my point remains the same. In some cases, for some models, these GPUs perform much better for testing than training. And then if we look at, you know, the look at BERT, for example, we have, we're back to normal or more normal results. So again, training, testing, and again, you guys can, this is going to be publicly available, so you guys can play around with this, and hopefully this will answer some of your questions. And of course, if you have any, you can drop them in the comments, and I'll be happy to answer those. Another really interesting thing here is, so precision, right? So we talked about single versus mixed precision. Mixed precision is huge, and then there's also quantization with a lot of the LLMs and these large models that are coming. Like Llama 7 billion. So it's important to think about mixed precision and quantization and those other kind of things. And as you can see, it really does make a difference. These don't have tensor cores and really don't have the ability to do those mixed operations. And you can see that there's quite a bit of performance lost uh, when we look at it strictly between mixed and single precision. So that is one thing to note here. Uh, you know, tensor cores are important, but at the same time, you also pay a premium for that technology. So you got to ask yourself, do you really need this? Again, what are your goals? Uh, you know, these things become really important, because you're talking about spending $800 for a single 3090, or, $160 at max for one of these two GPUs. So you just got to be careful that you're not overpaying for things you don't really need, and understanding what performance you're actually buying. All right, so I think that's a pretty good summary there. I also looked at data transfer. So this is basically, so this is data transfer time ratio. So basically, this is the total execution time, or rather, this is the amount of time it took to load the data onto the GPU versus the total execution time. So this is just a gauge of how much of your time did you actually spend just transferring data? And it's an important question because it can help you look at or help you identify bottlenecks. Um, and it can also help you understand, is it is it really like, do you really need PCIe 4? Do you really need NVLink? Do you really need these other more expensive and more performant data transfer technologies? So this is PCIe 3 that we're looking at here with my particular server. Um, and the only one of the GPUs I have that's PCI 4 enabled is the RTX 3090. And ironically, on average, it was actually had the longest data transfer time. So, um, and the caveat here as well is that these are external GPUs. So I have them with basically slim SAS extenders that goes to a like special piece of hardware that like boosts the signal and allows me to like keep the GPUs outside of the server case. For a time, I used actual PCIe extenders, and that's actually in a past video. I've upgraded since to the slim SAS cabling. I just haven't yet been able to make a video on that. But in any case, that could be a reason why the data transfer time is actually the highest here. Um, because the data actually has to go further. It has like a much more complicated route. Um, you know, but in theory, well, it doesn't really matter that this is PCI 4 PCI 4 enabled GPU because it's operating over PCI 3. But it, in reality, these should be basically the same. They should be close, unless there's some other internal reason for the GPU that these are just inherently slower in data transfer. But all that said, uh, what this says is PCI 3 is fine. I mean, you're looking at like 8% of your time you're spending transferring data on average. So, that's really not anything to worry about. If we're like, upwards of 10% or maybe like getting into the 20-25% of your time, okay, then, maybe it makes sense to look at why that's happening and then maybe look at, do you really need PCI 4 because you're having that much IO that's becoming a bottleneck for you. So again, these are just things to think about. And then again, here you can get more granular if you're interested, and you can say, okay, well, what happens if we're looking at mixed precision? Is there a difference? So mixed precision, for whatever reason, for two GPUs, it seems to spike up quite significantly. Um, for uh, for for other cases, um, doesn't really make that big of an impact. Okay, what about? Sorry, let me reset this. What about, what if we want to see, okay, is there a difference between training and testing? Okay, so let's look at training now. Okay, cool. So yeah, it looks like, I didn't see the legend, but basically it looks like on average, let me double check. No. So yeah, testing, it actually looks like has a much um, on average, we spend much longer transferring data when testing than when training. And that might be because the training or the testing operations happen so quickly that they're starved for data. And that actually causes, data transfer time to take more of the time, and the execution time is shorter. So the time spent transferring data is the same, but the execution time is less. So, there are all these different things that are just interesting to go through and look at here. And then, of course, you can uh, look at things by model. Sorry, let me reset. I think one of the interesting ones here is the LSTM. So yeah, this has on average a lot higher. And again, I think this is just because it's burning through these batches so quickly that uh, naturally a larger part of the um, overall execution time is going to be data transfer because the uh, data is processed really quickly. So again, interesting things, and you will have the opportunity to play with this and kind of answer your own questions. Whatever you have, and you can even add other things. You'll have the ability to change, um, this or download this, or I guess copy it to your um, you know Looker Studio and make some changes and do with what data whatever you want. Is I'll make all the publicly available. Um, all right, and then finally, I looked at memory usage. So, all right, guys, sorry about that. I forgot to average or make sure this is averaged, and then these were flipped, and it was just reading weirdly. Um, so what we're looking at here is initial allocated memory, and then initial reserved memory, and then steady state allocated memory and steady state reserved memory. So what does that actually mean? Well, just so whenever the model is loaded onto the GPU or GPUs, I'm basically pulling or dumping the memory data, memory usage data, just after that. So that's the initial. So basically, um, that is what is loaded, or what the model actually takes up. All of the uh, tensors and overhead and everything related directly to the model. So that's this. That is this allocated memory usage. That's what this means. And that's for the single and double GPU case. And then the reserve memory is everything that the GPU actually reserves in order to run. So not all of this is filled, but this is in case there's any overhead and to make operations more efficient, the GPU actually reserves excess memory than what it really needs. So basically, bottom line is this is what you actually need, or what the GPU is going to require you to use in order to actually run whatever operation it is you're trying to run for this particular for your particular use case. And then steady state is once you actually start loading batches, um, that's the memory. Basically, it once it reaches a steady state. So basically, after it loads the first batch, you're going to figure out what the um, what the new allocated memory is, and then what the new reserved memory is. So what you can see is, and these numbers seem a bit weird to me, but I've double checked them, and from what I understand, these are correct. But basically, this is what is actually being allocated for tensors and for all the things that are directly used to store the model and the batches. So that's a gig, and then a little over a gig for the double GPU case. Sorry, almost 2 gigs in the in the double GPU case. And then this is the amount that's actually reserved. So you can see that there's a huge difference in the amount that's reserved. So this is what you're actually operating with, and then what's actually being used uh, for like hard memory that's locked up for um, you know the model, the weights, the batch tensors, and all the other stuff. So I actually found this quite interesting. I didn't realize that this much extra memory was needed for overhead and for like computations and things by the GPU. So that was kind of a neat thing that came out of all this for me. I didn't realize this. Um, but yeah, so I thought this was pretty cool. And again, this just kind of gives you a better idea of how your GPU is actually using the memory that it's requesting and blocking off whenever you're going through operations. So, and maybe this is kind of interesting. Maybe you could, for in the case of LLMs, you could figure out how to reduce the memory reserved, and then you could actually operate on, lower memory, or operate with lower memory, so that you could, work with bigger models, bigger batch sizes, stuff like that. Um, so I have no idea if that will actually work, but that's just something I was thinking about. And then we could also look at something like, okay, is there a difference in, again, mixed precision? Does that really make a big difference for us? And then we'll go look at this. So yeah, it actually does. So you can see that with the single precision versus the mixed precision, we actually have a substantial increase or a substantial decrease when we are working with mixed precision. So that just kind of highlights the, especially when you're working with big models, if you can use mixed precision or quantize, it's going to significantly reduce the amount of memory you actually need, or the amount of memory that your GPU reserves. So, interesting find there, or interesting thing to look at there. And I probably could have done a better job of actually showing this across different precisions and things. So, this is a bit hard to see flipping back and forth between the two, but you get the idea. What I'm trying to show. And again, for tasks, so we could look at training versus testing. So training and then testing. So really not much difference at all there. And then again, we can look by model. Let me just reset again. And we can look at like ResNet. And we can see that, for your basic ResNet, you really don't need that much memory. You need like about 3.5 GB of memory, and then about 7 for 2 GPUs. So really not anything super crazy. Just about any GPU that you buy is going to have enough VRAM for that. If you look at BERT, okay, BERT BERT uses quite a bit more, and then the LSTM, it's basically almost nothing. And this is what I was saying. Like it's something's weird to me here. I don't know if I just didn't pick data sets or made the model too simple. So something strange here, but I do think it's still interesting to look at. But I do think more more digging is needed here on the RNN side to kind of understand like why this behavior is actually occurring. So, but anyway, nonetheless, I think it's worth presenting, and I think it's worth looking at this point. So, all right. Anyway, guys, that's pretty much it for this video. I was already way longer than I wanted it to be. So, glad I didn't go in any more depth, but please feel free to play around with all this data. I hope you find it useful. And of course, if you have any questions, please reach out to me or drop some comments in the video, and I'll be happy to answer those. But thanks again, guys. Really appreciate all of you guys watching. And just wanted to say thanks. I've recently passed 3,000 subscribers, and I really appreciate all of you guys watching and all of your support. So thanks again, and I'll see you guys in the next one.
All right, guys, brief reminder here. If you enjoyed the content, please consider giving me a like and a subscribe so I can continue to grow and produce better and better content for you. If you really enjoyed the content, you might even consider buying me a coffee, and the link for how to do that will be in the video description below. If nothing else, please just give me some feedback in the comments and let me know how I'm doing, if anything's unclear, or if there are anything that I can improve on. Thank you again, guys, and have a great rest of your day. Bye-bye.